All right, we can get started. Good afternoon. What's going on? Yeah.
Where's everybody?
I don't know.
St. Patrick's Day was Tuesday.
Yeah, it's awfully long time to have fun. So I'll try to cover as much as we can before we try to look at some other servers on Monday, right? So I'm going to continue with the quality of service and media server kind of notions because we need the notion of quality of service to sort of ground these notions of media service and stuff. And there are two important things you need to worry about. What happens on a single machine? If happens to be a media server, how do they manage their services and stuff like that? And the notion of how do you specify what the stream is and how do you access it from another network perspective, right? So first we're going to look at how do you manage it on a server basis, right? And it builds on what happens in an operating system. So you still have an operating system running on a machine, you're still trying to do the media, and all you're trying to do is do certain things which can make this particular scheme work for a multimedia, right? So multimedia, we expect objects to be requested often, so and the request to be heavy, so we want to make sure that can be serviced. So that's the goal, right? So in the last class, when we talk about media services, it's a very broad term. It's a multi-billion-dollar industry, and it involves a whole bunch of different parameters. It could be servers or like single server that you look at, or it could be a peer-to-peer based system or a hybrid thereof. It turns out you can't build an entirely peer-to-peer system, especially when they did a lot of analysis on these things. And one of the main reasons is, if you look at your DSL and stuff, it's asymmetric. You can download more than you can upload. So that means you can't fully have it sustainable purely by P2P, but you also have servers and stuff. So you have some sort of hybrid version where it's not just depending on one server, and then you have other services like IPTP, and we'll also see how voice over IP, which is the internet telephony system, works on building on top of this stuff, right? And before we talk about media servers, you have to understand how a specific application you're building is going to be used. If it's going to serve a single stream all the time versus multiple streams at the same time, right? So, and those have issues on how the system should be built. So if you have only one stream that is going to be streaming all the time, then you can expect given the amount of memory modern systems have, you can expect that the server could cache the whole thing in buffer and serve it out without ever going to disk. So you don't have to worry about the disk performance. You're essentially bounded by the buffer that you can hold, right? And even if you don't buffer the whole thing, if you're only serving one file, it's a lot easier to predict. Remember, one of the things from operating systems is if you can predict what you're going to do in the future, then I can do something. So if I know that you're going to request the next video frame, then I could maybe do prefetching or what have you. So even if I couldn't get the whole content in, I can do prediction, I can do better stuff, right? On the other hand, if I expect the media server to serve multiple objects, right, things become a little bit messier here because once I have multiple objects, then my prefetching has to compete against this different stuff, right? So I could solve them sort of by having multiple disks and having each disk per object. And if I don't do that, then I run into problems. So depending on where this particular application fits in, you run into problems, right? So when you think of something like YouTube, where hopefully Google has lots of servers, right? Lots of servers. Can they get away with using a single server per stream, or do you have to worry about multiple streams per server? Right. So Google has lots of objects, right? So Google means that they can't do. So they can't have one server service. So they can either have one server servicing all these videos, or they can have n servers servicing n videos, right? And basically send your request to the particular server, right? What would YouTube do, right? Would it have one server servicing all the videos, or one server per video, or some kind of a hybrid, right? The answer to that depends on how popular these objects are, right? And we'll see a little bit what that means. But essentially, the idea here is, if it turns out that all the objects that YouTube services are equally popular, then something like the single stream per server makes sense, because you have the popularity equal to the different objects. Most natural events, including media stuff, tends to follow a Zipfian distribution, right? How many of you heard the word Zipfian? Zip distribution. So Zip distribution is considered to be a natural phenomenon. This is how most of these systems in real life also work. Essentially, the distribution is sort of the So if you plot the object versus popularity, right? Typically, these things tend to have what is called a long tail, right? You have lots of objects, many objects which are very not popular at all. You have few objects which are very popular, and you have a lot of objects which are not popular. And over again, you tend to see this kind of a phenomenon where exactly how many objects tend to be here may differ by different systems, but you tend to have lots of objects which are not popular. You have few objects which are popular, right? What this means is you need to optimize for, let's say, these objects. And in practice, these objects tend to change. So if you think of a movie, the most popular one, if you look at the YouTube one, the most popular ones tend to be here, but they don't stay there forever in their life. So this week maybe something is popular, next week something else becomes popular, but you tend to have some things which are very popular here. So if you are a media server, you have to make sure that you can service these things. So you may have to have multiple servers to service this stuff. But then you also have a long tail, right? And so you need to figure out how to service these things, because there's so many of them, right? You can't just ignore them, because the sum total of all these objects is still large, right? So one of the challenges for these kind of systems is you don't use one of these other, you use a hybrid kind of system, right? So if you're a large media serving company, then you have to find out which one of the objects are popular. Try to make sure that they can be serviced really quickly in maybe one stream per server kind of stuff. But then you also kind of monitor these things. So you don't want to completely get rid of these things, but you try to make sure that these are the more popular ones are serviced all the time, right? So you use a combination of those in the media server kind of model. If you're using more like a home, some of the things we talked about, like a DVR or something, you don't have to worry about this thing because the number of requests are not that big, right? So that's one of the parameters we should look at when you're trying to look at a media server. The other important concept in the media server is the notion of, if you're going to store the contents on a disk, you have to make sure that you manage the disk properly, right? And that means you have to be placing the objects properly on the disk so that it can be serviced to you in a nice fashion, right? So if you remember from your operating system class, disks have two kinds of latencies, right? One is the seek latency, one is the rotational latency. The idea here is, the hard disks are made up of these platters which are spinning at a high speed, right? You have a magnetic head which is reading the contents, right? And the way it's built, the magnetic head can be moved. It can be seeked to any of the tracks, right? And so if you want to read, and the objects are stored on the tracks like this, like sort of like how you see on your CD. So if you want to, say, read this particular block, you have to move the head over to the right track, right? That's the seek latency. So it takes some time to move from wherever you are to the right spot. And then you have to wait for the disk to spin so it can come right under you. So if you want to read the stuff and the disk is spinning this way, you want to move your head to this part, and then you wait for the disk to spin right under you, and then you get the contents, right? So those are the two parameters that the if you're using a magnetic storage disk, you will have to deal with. So the challenge here is, and if you remember from the operating system class, we optimize these two figures for using a number of different schemes. So you try to make sure that, it turns out that the seek is more than the rotational latency. So you want to avoid the seeks, right? So what you don't want to do is, if you have to say read something here and something here, let's say you want to read something here on the innermost track, something on the outermost track, and something again on the innermost track, right? The worst possible thing you can do is, if you read the one on the innermost track, then seek all the way to the outermost track, then seek all the way to the innermost track, kind of thing. So you want to schedule these things such that you avoid the seek latency and the rotational latency, right? And in the case of media, it becomes even more of a problem, because while you are seeking, nothing is happening, so you're not able to service the video. Your quality of service goes down, right? And if you want to see what I'm talking about, go to a DVD and try to go between different chapters, right? Try to play use a DVD to go to the different chapters. DVD, if it is set properly, they're set up so you avoid the seek time. So you're as all the tracks tend to be in the sequential order in a contiguous fashion. So when it's playing properly, it reads all the objects in a particular track before going to the next one. So you hardly notice any noise, you hardly notice any speed problems. But if you try to randomly access frame 1 and frame 100 and all those things, then essentially your most DVD players cannot keep up with what you're trying to do, and you notice a tremendous drop in your experience. And again, you have to do the same thing for the media server, right? And again, it becomes more challenging, because if you have two different files that you're serving, then whatever optimization you have to do it for these two requests. They come interleaved, and you have to figure out how best to do it, right? So for example, when you write this stuff, in the case of a DVD, if I imagine only one movie, I can put them all in a sequential fashion, right? And let's say I have another movie, and they happen to be in a sequential fashion on a different part of the disk. Now, if I'm serving both of them at the same time, I would have to go to the next one, keep reading both of them. So I keep sequencing both of these points, and you run into the problem, right? So I did a good job of making sure that I can play one movie by keeping them all nicely set up where I don't have to do a lot of seeks. And I set the other one where I don't have to do a lot of seeks. But if I'm playing both of them at the same time, then I have to go from one region to another region, and I run into problems. Sort of things that you don't expect on the regular file system server stuff. Because in a regular file system, sort of like what you use on your laptop, you don't have timing constraints, right? So if you don't get the file quickly, things are kind of slow, but the movie doesn't stop, the video doesn't stop. In this case, those things stop, and you have to worry about those. So placement is very important in media server, right? I claim that placement is very important, right? Do you buy that? When is the placement on the disk not such an important task? How do you avoid having to pay the penalty for seeks and all those things? What is the technique that you would use to avoid having to seek back and forth?
You just cache it?
You cache, buffer, prefetch, what have you, right? So if I have some slack, if I know what you're going to do, if I can read all the stuff, then I won't have to pay the price, right? So the extreme would be, if I can put everything in memory once, then it doesn't matter, right? If I can put everything into memory, then I don't have to worry about all the stuff, because essentially I'm only worried about the worst case scenario, not the normal case. If these are the two movies and they can be kept in memory, then I don't have to worry about going to the disk at all, so it doesn't matter at all, right? Is that true for modern media servers, do you think? That everything can be kept in memory? No? Does anyone want to say yes? So one of the answers, one of the questions, the thing I say from my operating system class is, the answer is never absolute, right? It always depends, right? So what case do you say it's
You need a really big memory to fit everything in it.
Mm-hmm.
If you have, say, temporal dependence on something, on parts of the data, on the memory.
So that goes to the question of what is a typical memory, right? So you need a lot of memory, right? All these buffering schemes need a lot of memory. So without saying what that lot is, things are not clear, right? So what do you think is a typical hard disk size?
1 GB, 2 GB.
2 is the highest end, right? But practically 2 is also the most cost-effective space these days, right? If you look at the cost of the disk, right? If you look at the gigabytes per price per gigabyte, right? It turns out that smaller disks are actually more expensive, and 1 or 2 gig is a good size, right? So let's say 1 gig, right? And for laptops, I think it right now is half a terabyte is the sort of reasonable size, right? What is a reasonable memory for machine? What do you think is a reasonable? Reasonable, I don't mean like, so you're looking for the best price performance ratio, right? So you're looking for the best price per gigabyte, right? If you look at the memories, turns out, like let's say $20 is for 1 gigabyte, right? And if you say $40 for 2 gigabyte, right? And the memory tends to be somewhat like this. If you price out the memory, right, you tend to see somewhat price like this, right? If you ever looked at the desktop price, right? At some point, the price goes phenomenally high, right? So in this case, going from 4 gig to 8 gig goes to a lot of price because so if you ever built one of these machines, right? So if you're going to these bigger memory, you need a bigger memory chip, and that thing blows up, right? So maybe not 1,000, it goes to like a few $100s, right? So in this scenario, what would you consider is the reasonable, if this is the cost, what would you consider reasonable memory? I would consider the sort of like this one, right? For $50, you get like, so if you look at the price per gigabyte, that's actually lower than the one on the top, right? I think that nominal, the price at this, I think right now the reasonable price is like 4 gigabyte on a desktop kind of stuff, right? So if you have 1 terabyte disk and 4 gigabyte of memory, what would you say is the would you think that's enough memory to cache all the stuff? What else would this factor in? Going back to this 2 stuff, right? If you're doing 1 stream per server versus multiple streams per server, would that help make a decision? Let's go with the 1 stream per server, right? So all your server is going to do services 1 stream, and you have a terabyte of storage, and you have like 4 gigabyte of storage of cache, right? Would that be enough for you to not worry about stuff on the disk? No?
Well, doesn't it depend on the media that you have, the size of the media you have?
So it depends on the size of the media, right? What else does it depend on?
The speed of accessing the media from the disk.
Speed of accessing the media from the disk, okay. And what else would it depend on? There's another speed involved here which affects how good it is, right? It's the rate at which you can consume the stuff, right? The rate at which a network can consume the stuff, right? So if your client can take 1 gigabytes per second or something, then you need to worry about these buffers. But if your client is only getting it at DSL kind of speeds, then you have so much more. So you can kind of predict, and you can say ahead of the client, because your real bottleneck is the memory, the network connection to the client, so you can do a little bit more stuff, right? So, but anyway, so it points to the issue of like, it's not clear whether this has to be a problem because memory is getting bigger, disks are getting bigger, objects are getting bigger, and at some point, under some circumstances, like you pointed out, the placement is not that important, right? So if you look at the popularity curve, right, there are some objects which are not popular at all. So we can assume that if object is not popular at all, if you're watching a movie which came out in 1950s that 5 other people are watching at the same time in the whole entire world, right? You don't have to give, you can imagine not giving the best performance for those because people sort of expect them to be okay. And the top 10 list movies have to be serviced really quickly, so I can probably place them in systems where memory is plenty, so all of them is in memory, so you don't have to worry about the case. So the companies spend lots and lots of energy trying to answer this question, like how should we place this object, how should we do this stuff, right? So there are a bunch of researchers at HP Labs. I don't think we'll have time to read those papers, but they essentially try to figure this answer out, right? How do we make sure where to place these objects such that for a given amount of memory, given amount of cost I can run, I can make sure that all of them are happy. So they try to figure out how this popularity is and how these things evolve, and I make sure that. So what happens is these particular movies will get good service. These particular movies will get acceptable service. System is not designed for a random case, but for a specific case, and they iterate on the stuff, right? And usually we're talking about tens of thousands of machines at different locations around the world, and you're trying to optimize these things. And so in some cases, you don't have to worry about these things because the popularity of the object means that you're better off putting them on the disk, on the memory, and not worry about the disk at all. But in general, sometimes you have to worry about the disk, right? It's not as, I don't think it's as much as what you would have to worry about when this book was written, even a few years back, right? So in the case of so one of the techniques that people have used over the years for multimedia-based systems is the notion of a zone bit recording, right? So the idea here is if you take a normal disk layout, right, and there's a certain number of sectors. Traditionally, when you talk about it from the operating system perspective, one way so it turns out that the sectors which are closer to the spindle, which are the innermost tracks, they tend to have less area, right? So if you, let's say, have a sector which spans this area, right, the length that you get for that sector is a lot smaller than what you get from over here, right? If you assume the same angular velocity, for a given amount of time, the disk would either go from here to here or here to here, right? So if you do an equal distribution across the whole sector, whole disk, you tend to need much higher density recording in the inside of the track than on the outside, right? But that makes your algorithm simpler in terms of setting this system. So you end up having the same amount of number of sectors on all the tracks. That makes operating system easier to deal with because now if I say I want track 10, you do the math to figure out which track it should be, right? But you run into the problem that the tracks on the outermost edge are recording. So you take all this much space to, let's say, record 1,000 bits, whereas over here you only take this much stuff to record 1,000 bits. Your technology has to be able to record here. We are wasting all the stuff over here, right? The alternative to do that is to use a zone bit stuff where you use a constant area to store the sectors. So regardless of what you do, it turns out on the outermost track you have a lot more sectors. Innermost tracks you have fewer sectors, right? So this is kind of not so good from a perspective of using an operating system because now you have to worry about, so if you give me a track, I have to figure out where this particular track would land up on the different tracks. So my seek stuff and all becomes harder, right? But the nice thing about if I go with this model is I tend to have more sectors on the outside than on the inside, right? which means that I can place the more popular objects, store the more popular objects on the outside, because more popular objects, and so I can avoid the seek latency, meaning the time to move across the tracks, by pushing everything on the outside, right? So let's say I have 10 sectors over here and only 2 on the inside track. So if I'm here and I keep all my important files towards outside, then I don't have to seek as much. I rarely go to the center because center there is not that many sectors. So that's one way that I can avoid this problem by using a zone bit recording. It makes the things more complicated, but it also means that at one part of the disk on the outside, I have a lot more sectors, so I don't have to seek as much inside as I do outside, right? So that's one thing that was considered and that is quite popular. Change the way the disks are stored, and so you also end up using more of the disk, right? Because now you can store more sectors on the side, not just on the center, and you get more storage out of the disk. It makes things more complicated, but from multimedia perspective, this is good because now if I can keep the more popular ones on the outside, I avoid seeks as opposed to the the traditional model of storing the disk. And so since I rarely seek to a random point, I don't have to worry about the cost of figuring out where the things are, because since I'm only doing sequential, I don't have to worry about seeks all the time, right? So that's one technique that is used on the disk. You take the same disk that you had before, now you increase the capacity, increase the complexity, but that's okay because in the multimedia sense, the complexity is not the one that's going to kill you, but the increased opportunity to store more objects helps you more than the cost of the storing thing, right? So again, going back to the stuff I was talking about, in a disk, the things you worry about is the seek time, rotation latency, and the data transfer time. The data transfer time and the rotational time are fixed for a particular disk. So if you buy one of the SATA disk, they tell you how much data you can get out of the disk in and out. That's fixed by a particular hardware. Rotational latency is the 7200 RPM, 10,000 RPM, or whatever RPM that comes for your disk. That's fixed too. The seek time is fixed, but you have control over how much you pay for it, because that depends on how you place the objects. So usually you try to place these objects such that you reduce the seek time, because that's more under control. The rotational latency is also under control, but seek is the more important aspect, right? So there are a number of ways of doing the data placement on the disk. One of the useful things you can do is the contiguous placement, which is sort of what I explained for the DVD disk kind of stuff. You keep all the blocks next to each other, right? So if you have only one file in a particular disk, essentially you act like a DVD disk where everything is contiguous, but you have more than one file in a particular disk, right? So you have to figure out how to balance the notion of a contiguous and multiple files. So if I keep only contiguous, then I end up with all the, let's say, all file 1 on the outside, then file 2 and file 3 and so on, and then I have to pay the seek cost. So I don't want full contiguous, I want it to be interleaved somewhat, right? So one way I can do that is I can, instead of having the whole file, I can say 1 megabyte or 2 megabyte or 3 megabyte of a file is contiguous, and then the next file. So you can imagine, first 4 blocks of the first file, 3 blocks of the second file, 3 blocks of the third file, and so on. So you're getting the contiguous nature, but you're not paying the cost of completely keeping them apart on the disk. They're still kind of close together, right? Whereas if you have it in the non-fragmented, so if you're not contiguous, right, then this means that this object, the second file, has blocks all over the place. So if you want to do the sequential read, you may have to jump around, right? But in the case if you have 2 or 3 streams being sent from the same disk, there are conditions where this might actually work out to your advantage, right? So if it turns out that if this is how the disk is set up and you're trying to read all the 4 files at the same time, then you may be able to read, like sequentially like this and get the right amount of blocks for the different file, right? But in general, so you try to have one of these models. One is the contiguous notion, and the other one is you try to interleave. You try to be non-contiguous, but still try to. So it depends on what kind of a workload you're trying to look at, right? And again, the problem here is the intra-seek, seek between the different files. So as long as you don't have that, you can use a contiguous solution. But if you have to seek between different files, if you have 2 or 3 different files, you have to make sure that the seeks, because of the 2 or 3 different files, don't affect you as much. Right? And there are other mechanisms. Log structure is one of the things that you practice on in a grad level course. So the idea here is you store all the writes into the disk in a log fashion, right? You don't worry about placing the objects in contiguous fashion. You worry about the contiguousness of the write. So write works faster, but the reads don't work faster. So if you have to write file 1, the problem here is this. If you want to write the blocks from 2 different files, right? So you have the files, the blocks from here, the blocks from here, right? But if they come in at a certain fashion, let's say, they were written into the disk as so, right? So the users were writing these 2 files, each made of 2 blocks, but they were interleaving them for random reasons. So when I see it at the disk, I see it as one, block from one file, block from another file. If I want to make them contiguous, I have to rearrange them, have buffers and all those things. The notion of the log structure file system is, since I get all the stuff, I store them contiguously on the disk, because then my write is pretty fast. I don't have to seek anywhere. I write this stuff very fast. But when I try to read them, I pay the cost, right? So log structure file system, you don't pay the cost during the write, you pay the cost during the read, but depending on how you reorganize the disk, you can get the best of both, right? So while I'm writing, I can write it in the speed, in the way that it's fast enough. I can reorganize the file later to make these things contiguous again, right? So those are techniques that people tend to do to make these things go, right? You will notice them even in your normal desktops. If you try to do much of video encoding and stuff, you'll notice that if you don't pay attention to any of this stuff, you notice a lot of your seeking, right? The way you notice a lot of seeks is your hard disk, depending on how good it is, would go crazy with making noise, and that's one indicator of, if it's not seeking, you don't hear too much noise, but if it's seeking, you hear a lot of noise because it's trying to jump around, right? And so the yet another approach, and depending on how important these things are, you don't want it to be fully contiguous for all the stuff, but the other way is to do a statistical model of keeping them apart, right? So when you have multiple files that you're writing, you want them to be apart, but not by too much, right? So you're trying to avoid the case where you have first file over here and second file over here, right? So what you want to do is, you want the first file and the second file blocks to be within a certain range. So it may so happen that you promise that the blocks for the 2 files would be within a certain amount of range, so the cost that you pay is not too much, right? And it's not on a per block basis, but overall you try to keep them within a certain range, right? And again, there are a lot of other policies that you worry about, but essentially all of them boils down to the notion that for a given media server, you have to figure out how popular these objects are, how these popularities are, and you have to sort of predict how users are requesting these objects, which tells you how these, how do you place the objects in such a fashion that for a given request you would do a good job, right? And it's a traditional file system problem, which is when I store the file, I don't know how it's going to be asked. So I want to make sure that if I knew the popularity, I can place them in such a fashion that when you ask for it, I don't have to pay too much cost, in this case, seek time, so I get the right content to you. And one of the law is the zip law, which is considered the most natural for these systems. So zip law is very popular, very natural in most of the real systems, and it is good in some sense. There's some objects which are very popular, but it's also bad in another sense. There's a lot of objects which are not popular. You have to deal with both of them, right? And one of the and there are many systems on trying to how to optimize this stuff, and most of them are logical based on what the constraints were, right? So there's one system where they didn't use the zone bit recording, right? And they avoid the amount of seeks by keeping the most popular objects in the center and the least popular objects away from the center, right? So you keep the most popular here, second, third, fourth, and fifth, and so on, right? What's the why would you do something like this? Why do you think this will work? This is not the zone bit. This is the traditional scheme, right? Why would keeping the most popular one in the center help you? What's the intuition behind this approach? Yeah.
So no matter where you are on the disk, you're going to be most likely to go back there, and that'll be on average the closest.
Yeah. That's excellent. Yeah, on average, you expect to be half. I mean, in the worst case, you're half from the disk, right? You tend to be here, even for the least popular ones. You're only half point from the disk, right? And you can show cases where this works, right? You can also show cases where this will not work, right? Do you know where this this particular scheme will not work? What kind of accesses should the users do to make this scheme not work? So suppose I'm asking the first and the second most popular file. Would this work? Right? So if I'm asking the two most popular objects, these tend to be here, right? That means I only have to seek over here, right? So what would I have to ask to make this fail? Yeah, the two least popular, right? Because it's optimized for the most popular one, but the two least popular tend to be on the other end. And if you ask the two least popular one, this is the worst policy you can come up with for the least popular one, right? But it's okay, because if you look at this particular graph, right? If this is your stuff, the least popular ones are not that popular, right? So the likelihood that both of them are going to be asked is small. And even if they ask, there are only two users who are suffering. That's okay, right? You want to keep these people happy. So so again, you go back to the model, and if you're serving 1 million users and 5 of them fall into this 8 and 9 category, so be it. I mean, you're worried about the 1 million users, right? And then there are other ways to deal with this stuff. One of the things that we realize is disks are cheap, disks are practically free. So there's no reason why you have to deal with one disk and deal with only one head. The other way you can do that is have multiple disks, right? So you can have multiple disks and make sure that dynamically you place the objects on the different disks such that you get the best performance, right? So you're doing completely in software where you have two disks, they're independent disks, and I place the most popular one on one disk, or I place the disk object in such a fashion that I get good performance, right? Or I can use the RAID levels, right? And again, this goes back to operating system class. It's not very important what the different levels are. There are 6 different levels, right? So each level gives you a certain amount of redundancy, gives you a certain number of reasons why you want to use them to get more redundancy. But from the multimedia perspective, we don't particularly care about the redundancy part. We don't care about the backup part. We care about the part that these things have better performance, right? So I'll look at 2 RAID classes for now, right? RAID 0 is striping, right? Which means that if you have 2 disks, or let's say 3 disks, right? Actually, let's say keep 2 disks. 2 disks. Striping means that you basically go from 1 to, let's say, half a terabyte on this disk and half a terabyte to 1 terabyte on this disk. So you kind of glue these 2 disks together to get the capacity of a 1 terabyte disk. So this happens to be 500 and this happens to be 500 gigabyte, and together you get 1 terabyte, right? And this is awful from a redundancy perspective, because if one of them dies, both of them dies, right? From a multimedia perspective, what do you expect this system would give you, right? So from a multimedia perspective, you're trying to get data out of the disk as soon as possible, right? How can this help you in some sense to get better performance than what you can do with one disk? And how would you, let's say you have one media file that you want to be stored, right? I'm just naming it as 1, 2, 3, 4, 5, 6 blocks, right? Can I store them in some fashion where I get good performance? So in this case, there are two spindles, right? There are two independent disks, so they have two independent heads, right? So they can read two independent stuff at the same time, right? So can I use that to store this particular disk to get good performance? How?
Odd number blocks in one.
Yeah, some scheme, right? Odd number in one disk, even number in another disk. You can think of a whole bunch of stuff, right? So you can store odd number in one disk, and or you can store, certain combinations in one disk and combination in another disk. So now you're getting parallelism, right? Essentially, you're getting more parallelism out of the disk because you have two different things, right? And if I think of two different files, I can do the same thing, right? I can place them such that one disk is used for one file, another disk is used for another file, kind of thing. So these things give me more options in terms of how I can get the performance, right? So this goes beyond what we did for redundancy, because from redundancy perspective, this is awful because one disk crashes, everything crashes. But here we're not worried about reliability, right? Because hopefully these movies are available elsewhere. All you're trying to do is get good performance, right? So in this case, doing the striping actually gets you more performance because you are using the parallelism, not the reliability part, right? And the same goes for RAID 1, which is mirroring, right? Where everything over here is mirrored over here. So essentially, you can read from any one of these things to get the same content, right? Again, you get parallelism, right? So if I have the file stored here and stored here, so now I can do independently schedule them, right? So if this particular head happens to be closer to this block, this particular head happens to be closer. So I can figure out where I should move based on where those two disks, right? So from a multimedia perspective, you can do the same exercise for all the different RAID levels. But these two RAID levels are good enough because they get you parallelism in a very simple case, right? So you use the notion of a RAID to get the benefits that you really want by getting the parallelism. You're getting two disks to do the same stuff. So you can even think of having 3 disks or 4 disks, and that way you get more heads. So you can serve either more files or the same files, different blocks in different disks to get good performance, right? So some of the things that, like the striping, which is not really recommended for any other use, but tends to be useful in a multimedia scenario because now you have two disk comps to get the content from you. And the other aspect which we haven't really talked about so far is, we kind of mentioned, is the notion of a disk scheduling, right? And one of the things that you worry about in the traditional operating system is if you have the particular disk and you have a set of requests, somebody is asking for a certain number of sectors, right? The disk scheduling algorithm essentially tries to say that if your disk head happens to be over here, right, how should these requests be ordered in such a fashion that I get the fastest amount of time to get the contents out, right? So the idea here is if I need the content from here, I need a content from here, I need a content from here, right? And so the disk head has to seek to here, wait for the disk to rotate under it so you can read its stuff. Right? Seeking is the most expensive component, right? So the sort of the worst way to do this would be to request this object, and then this object. You're seeking all the way to the end, then seeking all the way to the middle and kind of things. So what you tend to do is you try to come up with a scheduling algorithm such that you can either go in one direction, you avoid the amount of seek distances, right? And the number of algorithms like SAN, CSCAN, and all those things, and the algorithms tend to be of the nature of you sort all the requests based on the tracks they're on. You sort them, and the variants are you tend to go in one direction. You keep going in this direction. All the requests which come to you, which are near that in that direction, you tend to service. So if you're at this location and then a request for inner sector comes in, you don't schedule it because you keep going towards outermost rim. So you go to the outermost end, you can either come back the same way or you can jump back to 0 and start again, right? So all these algorithms are designed to avoid the scheduling delay by essentially reordering the requests that come to you in such a fashion to avoid the amount of seeks, right? Now the problem here is, so those avoid the seek distances, but the price you pay for doing that is now you may have to wait a while, right? So if it turns out that the best policy is that I kind of stay within this outermost region, I never come to the innermost region because I have to do a lot of seek, then any object which is stored in the innermost sectors tend to suffer, tend to lose their deadlines. So you can imagine doing the disk scheduling, which is also aware of the real-time requirements. I want to optimize the scan the way the things are scheduled, but at the same time making sure that I don't have to spend too much time waiting for the stuff, right? And that's the notion here. You want to balance between the amount of seeks and the amount of and the time that you wait for the stuff, right? So you can imagine using a simple EDF, right? The earliest deadline first algorithm, where I make the disk blocks know what their deadlines are, and the earliest deadlines should go, right? And it will tend to be awful because if the deadlines are all over the place, then I'll end up seeking all over the place. So if the deadlines happen to be on the innermost, outermost track, then I happen to seek all over the place. So you don't directly implement earliest deadline first. What you do is sort of like a scan EDF, right? Scan EDF is you tend to go from the innermost track to the outermost track. The algorithm only keeps looking from the innermost to the outermost. But anything which is closest along the way, you sort them on the deadline first to get the best of both worlds, not just the deadline, but also the scan algorithm. Again, these are designed onto the multimedia disk itself to make sure that they get a certain amount of performance, right? So that sort of covers the notion of a file, the disk, and all those things, right? It's not clear how much of them are actually used in a modern disk, except when you buy hard disks, right? There are companies like Seagate sell hard disks for multimedia. So if you look in the market, they sell hard disks for enterprise, they sell hard disks for desktops, they also sell hard disks for multimedia, right? So hopefully, or presumably, those hard disks actually implement some of this stuff in terms of placing, doing these seeks and stuff, even though many times the operating system does not tell the disk what the deadlines are. But hopefully, since they're selling it for multimedia, perhaps the disk is optimized for a certain class of scheduling, right? So that sort of covers the notion of a disk. And again, the importance that we place on the disk is it's not as important now because the memory tends to be large, but it's still one important aspect, right? Before I leave, I'll kind of give a preview of what we'll look at in the next lecture. I was hoping to get to this by today's lecture. Is the notion of so now that we sort of know something about networking. We know networking has like wireless and packets and all those things. How do we make the networking work for multimedia, right? So how do we make these packets not just some packet, but be aware of multimedia kind of stuff? And the sort of techniques that we look at is RTP and RTCP. There are a lot of acronyms in this particular in networking in general. So real-time protocol where you kind of tell the packets to have certain real-time constraints, and the corresponding control protocol for that is RTCP. So that lets the server and client know something about the quality of the network packets that they're getting. Then we also introduce a notion of a session, which is higher level primitive, which sort of says what's going on, prioritize between the different RTA, RTSP kind of stuff. you kind of encapsulate these requirements in a SDP file. I'm saying all this stuff because in the media server, when you look at it, you have to configure these things because these are important parameters. So SDP file tells you all the parameters that a particular stream is going to negotiate. So that's how you negotiate your RTSP. And another important protocol is the SIP protocol, which is part of the voice over IP, right? Think of this as if I use voice over IP and I want to use that as a telephone call, right? I have to call you, right? In the regular phone, I don't call you, I call the phone number, and the phone number is something that is wired into your jack, right? So if I call your home, I don't call your phone, I call your home, and the telephone company wired it such that the calls go anywhere in my house, and any phone which is connected to my house gets the call. When we talk about an internet-connected IP, there is no such notion. I can connect anywhere, I get an IP address, but I need to talk to the human being. And SIP is a protocol which lets me call an endpoint, not because in the internet protocol world, everybody has an IP endpoint. I don't want to call IP address, I want to call you. So I want to say you or something. So that's the way you get the notion of a numbers or something to call in the voice over IP world. So I think this is an interesting protocol. And the SAP is the multicast announcement protocol. And all this problem is, how do you know where things are, right? You know YouTube is there because go to www.youtube.com. But suppose I'm broadcasting this particular lecture somewhere. How do I advertise it? How do I tell you and all those things? And one of the important protocol is SAP, which basically lets me broadcast or tell everybody what I'm doing. Not like you're going to a web page, but essentially saying this is what I'm trying to show, and broadcast announcements so that anybody can join or participate, right? So these are the different protocols we'll look at. Unfortunately, I didn't get a chance to go through that stuff, but so we can look at how media servers sort of play with this stuff before we go through lecture on that stuff, right? And if you have any questions about those, stop me before we start to do a demo on Monday, right? I'll see you guys on Monday.